Hello everyone, Kotongwane, the native god here. Right, we are still looking at relative velocity, but now I want to take you through how we approach problems where we've essentially been given the relative velocity or the resultant velocity, right? And in such cases, that is where we are asked to determine either the velocity of the object or the velocity of the frame of reference, right? As always, you first have to look at the statements and then read the question thereafter, right? So that you know what exactly we are looking for, right? So let's read the statement to see what we've been given and then look at the question to look at what we are looking for, right? The question reads as follows, or the statement reads as follows. The velocity of object P is 120 kilometers per hour east, while that of object Q relative to P is 234,307 kilometers per hour west, 33,671 degrees north. The direction of object Q is north 30 degrees west, right? Now, as per the statement, we've been given the velocity of object P as well as its direction, and we are given the relative velocity. So in this case, we are given the resultant velocity. Our resultant velocity is such that it is Q relative to P, right? And this is its magnitude as well as its direction, right? Now regarding object Q, we've been given its direction. It is headed north 30 degrees west. The question is determine the velocity of object Q, right? Now we've been given the resultant velocity, which is the velocity of Q relative to P, right? This here, the resultant velocity, right, it tells us which of the two objects we are going to take as the object and which one we are going to take as the frame of reference. So Q being the first letter means that Q, right, for this case is the object and P is the frame of reference, right? Now what are we looking for? We are looking for the velocity of object Q. So essentially we are looking for VQ. Right, so that is what we are looking for, right? So now let us represent the given vectors on the Cartesian plane, right? We are given the resultant velocity, which is the velocity of Q relative to P, right? It is headed west 33,671 degrees north, right? So this angle is referenced from west. West is on the x-axis, so that means that this angle is referenced from the x-axis, right? And headed north, it means that it is on the second quadrant, right? So this is west, right? This here is west, right? 33 degrees, 33,671 north. So 33,671 north, headed north, right? So this is going to be somewhere there, right? So this here we will have our resultant velocity, right? And this, the angle here is 33, so the angle is 33,671. That's our angle here, 33,671. Right, that's in degrees, right? Now, of course, our resultant vector here is oblique, right? So we have to resolve it into its components. So resolving this into its components, right, we are going to have a vertical component as well as a horizontal component, right? Horizontal component, right? So vertical component is headed in that direction, horizontal component is headed in that direction, right? Now remember that this here is the resultant, right? So the vector here, the original vector, is the resultant, right? Now remember that had we not been given the resultant and we had to calculate the resultant, meaning we are given the velocity of q as well as the velocity of p, and we had to determine the velocity of q relative to p, which would be the resultant for this case, right? If we were to use, or in using the method of components, what we would do is apply conditions of equilibrium. In applying conditions of equilibrium, we would first have to calculate the components of the resultant, right? The components of the resultant being the sum of the velocity of q relative to p in the x direction, as well as the sum of v of the velocity of q relative to p in the y direction, right? Now, what does that tell us? That tells us that how we denote the components of a resultant velocity is, right? The components of a resultant velocity in the y direction are the sum of v q relative to p, right? Remember, in this case, q is the object, p is the frame of reference, right? So as far as the components of the resultant velocity, in this case in the y direction, that will be the sum of vqp in the y direction, right? And this will be equal to, now this here, right, vqp is equal to 234, 307, right? So this here, you look at its direction, it's headed north, so we take it as being positive. So this will be positive 234, 307, right? Our angle is referenced from the x-axis, hence the y component will be represented in terms of sine. So sine 33,671, right? And then we get the x component, right? Now, as per conditions of equilibrium, the x component of the resultant we denote as the sum, right? We denote as the sum of v q relative to p in the x direction, right? Now, if we look at our x direction, right, the x component of the resultant is headed west. West we take is negative, so this will be negative 234, 307, right? Again, our angle is referenced from the x-axis, hence the horizontal component will be in terms of cos. So this is cos 33,671, right? And that is our what is this? The horizontal component of the resultant, right? So we have the resultant, and we have P, which is our frame of reference. And remember, for relative velocity, the frame of reference we draw in a direction that is opposite the one that you've been given. So originally, P is headed east. Opposite of east is west. Right, so we draw this headed west. So that's headed in that direction, right? Remember that seeing that we're using the method of components, right? We will take P, seeing that P is parallel to the x-axis, right? It is not an oblique vector, hence we do not need to resolve it into its components. It means that we are going to take P as its component, right? So seeing that this is parallel to the x-axis, then we are going to take P, right? So this is VP. We are going to take VP as its component. So seeing that it is parallel to the x-axis, it means we are going to take it as its x component, right? So this is equal to, this is headed west. West we take as negative, and the magnitude is 120. So this is negative 120, right? Now we've already been told that the velocity of Q, which is our object here, right, is headed north 30 degrees west, right, which will be in this quadrant, which obviously makes sense, right? So this will be somewhere there, right? This will be somewhere somewhere there, right? North, remember this direction specifically is a reference from north. North is on the y-axis, so it means that this angle is a reference from the y-axis, right? So this here, right, so this here is north, right, 30 degrees west, right? So this angle here, right, so that angle is 30 degrees, right? Right, so you expect that the velocity of q will be in this direction here, right? We've been told that it is in that direction, right? But I'll show you how you would calculate that direction of either the object or the frame of reference, right? I'll show you how to calculate it, right? They don't necessarily have to give us its direction, right? But in this case, they made things very simple for us. They've given us its direction, meaning that we only have to calculate its magnitude, right? Right. Now let us calculate the magnitude of q, right? We take the very same approach we would take for any problem based on relative velocity using the method of components. We apply conditions of equilibrium, right? Applying conditions of equilibrium, we say the sum of v, the velocity of q relative to p in the x direction, is equal to vq in the x direction plus vp in the x direction, right? Now in this case, we do have this here, right? We have the velocity of qp in the x direction, right? It is equal to this here, right? So we substitute. This is negative 234, 307, right? Cos 33,671, and this is equal to vqx, which is what we are looking for, right? For this step, we don't have this, plus vpx, which we do have. It is equal to negative 120, right? So we're looking for vqx. So we then transpose this to that side, right? Hence, leaving vqx as our subjects of the formula, right? Once you transpose the 120, it becomes positive this side. So then you're left with 120 minus 234,307 cos 33,671, right? And here we get negative 74,998. This will be in kilometers per hour, right? Remember that this here tells us of the direction, right? So seeing that this is a horizontal component of q, right, it means this here is headed west. So this is 74,998 kilometers per hour, right, west, right? So we have the x component of the velocity of q. Now we calculate the y component of q, right, by again applying conditions of equilibrium, but now using the components of the resultant in the x direction, in the y direction, sorry. So this here is the sum of vqp in the y direction, right? So this will be vqy plus vpy, right? We have, remember in this case we do have this, right? This here is the component of the resultant. The component of the resultant in the y direction is equal to this one here, right? So this will be 234,307 sine 33,671, right? Remember this one is positive, right? We are looking for this, we don't have this, right? Plus vp, right? Remember vp is parallel to the x-axis, hence we took it as a component of p in the x direction, hence we do not have the velocity of p in the y direction, so we take it as being approximately equal to 0, right? Therefore that means vq in the y direction is equal to the 234 307 sine 33,671, right? Which, if you punch in your calculators, right, if you punch this in your calculators, you are going to get 129,905 kilometers per hour. Seeing that it is positive and parallel to the y-axis, it means that it is headed north. All right. Now we have the components of VQ, right? Now we can use Pythagoras to get exactly what it is that we're looking for. We are looking for VQ. So using Pythagoras, right, VQ is equal to its x component squared plus its y component squared, right? Its x component is VQX squared plus VQY squared, right? This is what we are looking for, right? This here will be equal to, now we substitute, right? Now we substitute. VQ in the x direction is equal to 74, so this is 74,998 squared plus the 129,905 squared, right? So that means VQ is equal to, now if you punch this in your calculators, we are going to get 150 kilometers per hour, right? Now we've already been told that this is headed north 30 degrees west, right? Also, this here tells us the components or the direction thereof, also told us the direction, right? Now let us see how we would determine this angle if we had not been given it, right? So had we not been given this angle, right, all you do is you would have used tan theta. Tan theta is equal to the component of Q in the y direction divided by the component of Q in the x direction, right? So to get theta would have been equal to the arctan of VQY, which is 129,905 divided by VQX, which is 74,998, right? Now punching this in our calculators, right, the arctan of 129,905 over 74,998, right, and we get this here would be approximately equal to, so theta would be 60, right, 60 degrees, right? Remember that this here, seeing that it is in terms of the y over the x component, right, it means that this here is a reference from the x-axis, right? So this VQ would be 150 kilometers per hour, right, using the angle that is referenced from the x-axis, right? So we look at the component of VQ in the x direction, it is headed west, so meaning that the 60 degrees is a reference from west, the angle is 60 degrees headed north, right? Or if we were to express it the way that they have, right, in terms of the angle being referenced from the y-axis, so this would have been 150 kilometers per hour, right, north. Now obviously if we were to reference the angle from the y-axis, you would then say 90 minus 60, which is 30. That is where the north 30 degrees west comes from, right? This is the approach you would take if in a problem where you are given the resultant velocity and one of the object's velocities, and you are supposed to determine the velocity of either the object or the frame of reference. This is the approach you would take using the method of components, right? Now try doing the same problem, but using the vector diagram or parallelogram method. Right. Hope you find this helpful. If you did, please like and subscribe on the channel so that you do not miss any other content that I'll be uploading in the future. Right? Engineering science is a fun subject. Right? You just need practice. You need to look at it from a conceptual perspective. Right? It shouldn't be enough that you do problems to get answers. Right? Try understanding the work. If you understand the work, engineering science becomes fun. Right? Right. All the best. See you on the next one.